Least squares regression. More about the linear relationship between variables. Module 3, Part 4. Our objective in this lesson is to find the least squares regression line and use the line to make predictions. If you have a TI-84 calculator, print the slides or play the PowerPoint so you can follow the directions as you enter the data. I will be skipping through those slides in this video since graphing calculators are not required for this course and it makes the video longer. This is the part of the class that uses some of your algebra background that involves equations of lines. In previous lessons, we just eyeballed the linear relationship in a scatter plot. Now we want to find the equation of that line. The slope-intercept form of the equation of the line is y equals mx plus b, where x and y are variables in the equation. The slope is represented by m, and b is where the line crosses the y-axis. The slope tells you how steep the line is. If it is positive, the line goes up. If it is negative, the line goes down. If you know 2 points on the line, you can find the equation by first finding the slope with the slope formula. M equals y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. So the change in y divided by the change in x. Then you pick either of the points as x1, y1 in the point slope formula to find the equation of the line. And the point slope formula is y minus y1 equals m times x minus x1. Let's review with an example. Find the equation of the line through the point 25 and the point 49. First, find the slope. So we have 9 minus 5 over 4 minus 2 equals 4 over 2, which reduces to 2. Notice if I choose 9 from this point to be the first y value, I have to choose x from that same point to be the first x value. But it doesn't matter which one you choose. I could easily have done this as 5 minus 9, and then if I go 5 first with the y's, I have to use the 2 first with the x's. This gives me a negative 4 divided by a negative 2, which still reduces to a positive 2, so you're going to get the same slope. Then you pick either of the points as x1, y1 in the point slope formula to find the equation of the line. And you will get the same equation whichever point you pick. So I use the point 25, so I have y minus 5 is equal to the slope, which we found was 2, times x minus the x coordinate of that point, which is also 2. That gives us y minus 5 is equal to 2x minus 4, and y equal to 2x plus 1 is the equation of the line. To check your arithmetic to make sure that you didn't make any mistakes, it's not a bad idea to take the point you didn't use, which in this case is 4, 9. Plug it into the equation and see if the arithmetic works out correctly. Is a good way to catch any arithmetic mistakes. And 2 times 4 is 8 plus 1 is 9, so that looks correct. Now let's apply this to a set of data. Using the following sample data, find a linear equation that relates x, the explanatory variable, and y, the response variable, by selecting 2 points and finding the equation of the line containing those 2 points. So if we eyeball the scatter plot, it looks like that line fits pretty well, and it looks like that line maybe goes through the points 2, 5.7 and 6, 1.9. So we're going to use those just like we did in the previous example and find the equation of this line that you see there. So first we're going to find the slope using the slope formula, and we calculate that to be negative 0.95. Then we're going to use the point slope formula to find the equation of the line. So we're going to pick either one of those points for our x1, y1 values, and we're going to use the negative 0.95 for the m, which is the slope. And I use the point 2, 5.7, so I put the 2 in for x1 and the 5.7 in for y1, the slope of negative 0.95 in for the m, and just simplify. So that gives us an equation of y equals negative 0.95x plus 7.6. And this is what the equation looks like graphed with the points on the scatter plot. Use this equation to predict y if x is equal to 3. So what we would do is put 3 in place of x into our equation that we just found and do the arithmetic. So that tells us if we plug in 3, the y value that goes with it is 4.75, and we would call this the predicted value. Because we used our line of best fit to predict or guess what the value of y would be if x was 3. When we find a regression line, we can use it to make predictions. We will then have some actual data values, which are called observed values, that we collected, and some predicted values that we get by putting values into the regression equation. The difference between the observed value of y and the predicted value of y is the error or residual. It is a measure of how close the predicted line is to the actual data. Using the line from the last example and the predicted value at x equals 3, we find that error or residual by taking the observed y value, 5.2. If you go back to the table, you'll see that. The predicted value we found when we plug 3 into the equation, and that difference is 0.45. So what that means is the vertical distance between the diamond, which represents the point we actually collected, and the point on the line is 0.45. That's how far off we are. The residual tells us how far off we are if we use the line to estimate the value instead of the actual data point. You can think of the line as the average value when we have two data sets. Now obviously we don't need to predict where we already have collected data, but we might want to make a prediction, say from this data it doesn't look like we had a data value at 4, so we could use this line to predict what we think would happen at 4 based on this relationship. The line of best fit is the line that is closest to the data as determined by finding the residual for every data point. You will be happy to know that software does this for all possible lines and spits out the line that best fits the data. But I am a firm believer that you should know the idea behind something before you rely on the technology. In this graph, the dots are the actual collected data points. These little lines represent the distance between the data point and the line, how far off it is, and those are what we call residuals. The previous slides show you the math involved in finding trend lines or regression lines. It is one use of something you learned in algebra. Most of you will be happy to know that we will use technology to find regression lines, but seeing the process once should help you understand what the technology is doing for you. It is much better at finding the line that fits the data best than we would be doing it by hand. Use the drilling data to find the least squares regression line, predict the drilling time if drilling starts at 130 feet, and then answer the question, is the observed drilling time at 130 feet below or above the average? And notice we collected, this would be our observed value for 130 feet. Then draw the least squares regression line on the scatter diagram of the data. If you don't have a graphing calculator, use the Schroeder site. Now stop the video until you finish working this problem. Using the Schroeder site, we have the scatter plot with the regression line on it, and it gives us the equation of the regression line along with an R value of 0.773. So a moderately strong relationship exists. And I'm skipping over the calculator slides. Now we're going to agree to round the estimates of the slope and intercept to 4 decimal places. So y hat is going to equal 0.0116x plus 5.5273. Notice that the equation from the Schroeder site agrees with this equation, but it's rounded to 3 decimal places instead of 4. The caret symbol over the y is read y hat, and this tells us that it's a regression equation and we can use it to predict outcomes. Predict the drilling time if drilling starts at 130 feet. Since drilling depth is an x variable, all we do is plug 130 into that equation and do the arithmetic. That tells us that the predicted value for 130 feet is 7.035. Is the observed drilling time at 130 feet above or below average? So if we go back to the data, we remember our observed drilling time was 6.93 seconds. The drilling time predicted by our regression line is 7.035 seconds. So the drilling time of 6.93 seconds is below average. Average is the point that is right on the regression line for that drilling depth. So average at 130 would be 7.035. And this is the scatter plot with the line graphed on it. Caution: if the least squares regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, we say the researcher is going outside the scope of the model. Never use a least squares regression line to make predictions very far outside the scope of the model, because you can't be sure that the linear relationship will continue to exist. Here's some more data. Here we want to find out if there is a relationship between fat grams and total calories in fast food. Can we predict the number of total calories based upon total fat grams? So stop the video while you work this problem. Here's our scatter plot with our regression line. We have an R value of 0.975, so there appears to be a strong relationship between these two variables. So it should be pretty safe to use our regression equation to predict. Predict the total calories based upon 22 grams of fat. First, we notice that we do not have an observed value for 22 grams, but 22 grams is between observed values. Since this is within the scope of our model and the relationship is strong with an R value of 0.975, we're pretty safe in making this prediction. So we take our regression equation and we put 22 in for the x. We do the arithmetic and we find out that our predicted value, which would be a y hat, is 451.934 calories. Based on the model from our sample data, we predict the number of calories in food containing 22 grams of fat would be about 452 calories. And again, I'm skipping the calculator information. Some notes on correlation. In this class, we use the correlation coefficient R as a measure of the strength of a linear relationship between variables. The sign of R let us know the direction of any relationship that existed. You may have noticed that the calculator and other software packages also report an R-square value. R-square is the proportion of the variation in values of y that is explained by the least squares regression of y on x. For example, if R equals 0.704 for a given set of data, then R squared would be 0.496. This means that only about half the observed variation in data is explained by the straight line pattern. The other half of the total variation is due to other factors. A higher level statistics class would study R squared in much more detail. R gives us all the information we need for this course. Now take the Module 3 Part 4 assessment of learning. The password is line.